Before proceeding to some more physics of particles, we should take a first look at a very important piece of mathematics. The set of the eigenfunctions that we looked at for the particle in a box problem, that's a set of all sine waves with integer numbers of half waves fitting between the walls. This set of functions, like other sets of eigenfunctions we will find later, has a remarkable mathematical property. That property is called completeness. This property of completeness is one that you may have come across informally without actually knowing it. Certainly, if you've ever dealt with the mathematical topic of what is called Fourier series or Fourier analysis, you will have seen this idea more formally. A good example of it is the movement of an audio loudspeaker. And I've actually got an audio loudspeaker here, and we'll take this apart in a minute and have a look at it. This can be described in terms of either the actual displacements of a loudspeaker cone at each successive instant in time, or equivalently in terms of the amplitudes and phases of the various frequency components that are going to make up the music being played. So let's look at this loudspeaker here. This is a simple computer loudspeaker, and we can take this thing apart. And down inside here is the actual loudspeaker cone. And when the sound is coming out of the loudspeaker, the cone is going in and out. It's being driven by the magnet at the back and the current flowing through these wires here. And obviously, all the sound results from the movement of this loudspeaker cone. It radiates acoustic waves out in front of us. Now, we can think of this movement in space back and forward of the loudspeaker cone as just simply a series of displacements back and forward. But you know from listening to music that you can also think of sound in terms of a set of tones, of a set of different notes. And it turns out that those two descriptions are actually both complete descriptions of the displacement of the loudspeaker cone. So, loosely speaking then, with the loudspeaker cone, different frequencies are different notes. And we can think of the sound from that loudspeaker either in terms of the position in time or entirely equivalently the set of frequencies that are coming out of the loudspeaker. Both of these descriptions are what we can call complete. Any conceivable motion back and forwards of that loudspeaker cone can be described by either. So formally, we can change from a position as a function of time description to a set of different frequency components with different amplitudes. And also, we have to know the phases of those different frequency components, where in the sine waves start. And we can do all of that formally by the technique of Fourier analysis. We can convert from one of those ways of talking about the displacement of the loudspeaker cone to the other by the technique of Fourier analysis. And the way of representing the motion in terms of these frequency components, in that case, is called a Fourier series. Now, the specific details of Fourier analysis are not going to concern us here, though that whole subject will turn out to be just a special case of the more general mathematical ideas that we're going to set up. If we think about the eigenfunctions of that particle in a box problem, they have this property of completeness in the following sense. If we had any function at all that fits between these two walls and that formally hits 0 on the two walls, then we would find that we could write it as a sum of various of these eigenfunctions with different weights on the different functions in the sum. So we might have just a small amount of the first one and quite a large amount of the second, and so on. Hence, this mathematical set of eigenfunctions can be used as just as complete a way of describing any function that fits between these walls as would the description in terms of the heights of the function at each different horizontal position. This concept of completeness will keep coming back in our mathematics here, and we're going to find it's a very general and very powerful property of the sets of eigenfunctions we will come across.
So let's look at this idea of Fourier series. Suppose we're interested in the behavior of some function, and that's going to be, for example, the displacement of a loudspeaker cone. That's the thing that generates the sound that we can hear in music or whatever. And we're going to presume we're interested in this from some time 0 to some time t0. And we're also going to presume here that this particular displacement starts at 0 at time 0 and ends at 0 at time t0. Then an appropriate Fourier series description of this would be this form we have here. That is, we're saying that any function f of t can be written as a sum of sine waves, a sum of different frequency signals, as it were. And these different frequency signals, they all differ by a particular factor in frequency here. So this first sine wave with n equals 1 is just one that goes up and back again. The second one with n equals 2 is one that goes up and down and back again, and so on. We're saying that if we take a collection of these sine waves, put appropriate weights in front of them, add them all up, they can describe any function f of t that starts at time 0 at 0 displacement and ends at time t0, also at 0 displacement. Now, we're not proving this, but this is a remarkable kind of result here, and we'll be working more with this concept as we go forward. Of course, we have to figure out these amplitudes here, and we'll show later how to do that. There's a quite general way of figuring these things out. And these amplitudes, an, as I said, are the amplitudes of these different frequency components. So any function in time with these properties up here can be written as a sum of functions of different frequency and equally spaced in frequency by the amount given by this expression. So mathematically then, if instead of talking about a function f of t, we talked about a function f of z, of position, and now instead of talking about time from 0 to t0, we're saying let's talk about position from 0 to lz, so we're looking over a distance lz. And again, we're going to presume that our function starts and ends at 0 height at these two ends. So, similarly, we can write this in the same kind of a way. We've made no change here other than writing z instead of t and lz instead of t0. So what we're saying is that any function f of z that has these properties can be written as a sum of sine waves again. And we have to figure out these coefficients in here, but we will do that later on. And again, for some set of amplitudes, we're going to have to work out these ANs here. Now, we remember our set of normalized eigenfunctions that we happened to get from solving the problem of the particle in a box. And you see that these are also just these same sine waves. They've got another constant out front, but we can deal with that fairly easily. So with a minor change, we can use these functions, these eigenfunctions of the particle in a box problem, instead of the sine waves. That is, instead of writing our expression in this form with an times some sine waves, we can write it as bn times these eigenfunctions. All we'd have to do is replace the an here by a bn, that is the square root of lz over 2 times an. So we're saying that any function f of z between 0 and lz that hits 0 on these two ends can be written as some of these eigenfunctions multiplied by coefficients in front. This function here does not have to be a solution of the particle in a box problem. This is a mathematical statement that any function between 0 and lz that hits 0 on the walls can be written as a sum of these eigenfunctions with coefficients in front. So we can restate the same mathematics in new words. We can say, with our function f of z equal to this summation here over these eigenfunctions, that it is now the expansion of f of z in the complete set of normalized eigenfunctions. This is exactly the same thing as the Fourier series we just wrote down. It's just another form of words for expressing that. And note that though we've illustrated this by connecting to Fourier series, this will work for other sets of eigenfunctions also. This is a very powerful property of the sets of eigenfunctions of a very broad class of problems. They form complete sets, which means that functions can be expanded in them. And this is a mathematical statement. These functions don't have to be solutions of a particle in a box problem or some other problem. This is a mathematical statement that any of these functions can be written in terms of these eigenfunctions of some possibly other mathematical problem. It's a very powerful property of sets of eigenfunctions of a very broad class of problems. So we can talk about a new language. We can talk about basis sets of functions. A set of functions such as these psi n of z here that can be used in this way to represent some other function f of z is referred to as a basis set of functions. Or more simply, we might just say a basis. We might be a bit lazy there. And this set of expansion coefficients, as we now call them, these amplitudes Bn, is then the representation of f of z in the basis psi n of z. What we're saying here is that any function f of z can be represented in an appropriate complete basis. It's just as complete a way of writing out this function to write down these expansion coefficients on this basis here.
So we are saying that instead of writing out the function as a set of amplitudes in space at different positions, we can just as well write it out as a list of the amplitudes of these basis functions. If we add up all of these basis functions, whatever they are, like our sine waves in the particle in a box, with their appropriate amplitudes, the heights of all of these different waves that we're going to put in there, our expansion coefficients, or those amplitudes, we will get back to exactly the same function. Because of the completeness of this set of basis functions, this representation is just as good a one as the set of amplitudes at every point required to specify or represent the function in ordinary space. A key point is that the eigenfunctions of differential equations are very often complete sets of functions. And very importantly, the sets of eigenfunctions we encounter in solving physical quantum mechanical problems are complete sets, which is mathematically very useful. Of course, the ordinary sine waves themselves are in fact the solutions to a differential equation of that appropriate type. And if you like, that could be regarded as a proof of why Fourier series actually work. We are not going to go into the formal proof of why the sets of eigenfunctions of certain differential equations form complete sets. That requires more mathematics than we have time to discuss. But it is a very powerful piece of mathematics.